we talked about using transistors or analyzing circuits with transistors under DC conditions. Then we looked at the small signal behavior. We showed that you can actually make transistor amplifiers with a device that is in active region. Throughout the whole discussion there, we assumed the device was in active region. We said that, okay, if it is not in the active region, a device that is in cutoff or saturation or triode regions, it doesn't respond to the input variations, right? So in order to have that sensitivity to input, we want to keep the device in active region. Now, we did the small signal analysis, figured out what is R in, R out, AV, AI in all those cases, or at least 3 basic amplifier stages. But then the assumption was always that the device is biased. And what does it mean by biased? It means that you get the desired GM from your device. And how do you figure out the desired GM? Well, if you want gain, GMRC gave you the gain. If you wanted input resistance, GMRE was affecting the input resistance, or 1 over GM gave you the output resistance. So GM is usually the parameter that you will first calculate after you're given a set of, let's say, requirements for gain, input resistance, and output resistance. So they tell you that, we want an amplifier with a gain of 100, input resistance of 10 kilo ohms, and output resistance of 5 ohms. You think about the topology of the amplifier that you want to use. The output resistance is too small, so I should probably use a common collector stage there, but then I don't get the voltage gain. I have to use maybe a common emitter or common base stage at the input, but the input resistance they give me is 100 kilo ohms. So common base is not really that good in terms of input resistance values. If I want to do this whole work with just the minimum number of stages, maybe I should use a common emitter at the input and a common collector at the output. Now that you have decided the topology, then you think about, okay, so if the output resistance is 10 ohms, well, a common emitter stage or common collector stage that is biased at 2.5 milliamps will give me right away. So, a 10 ohm output resistance means 1 over GM is 10 ohms, right? Or GM has to be 1 over 10 millisiemens, and therefore the current is 2.5 milliamps. So I jumped a couple of steps there. So right away I have a value for GM, which then determines the current for that stage. For the preceding stage, same thing, right? We go through the analysis. It may not be as easy because you want some gain as well as the input resistance from that stage. But usually GM is the first parameter that you calculate for your stage. And for both MOSFETs and BJTs, we saw that GM depends on the biasing conditions. For a BJT, it is straightforward. It is just IC over VT. For a MOSFET, it is ID or 2ID over VGS minus VTH. So not only the current, but also the voltage difference between the gate source and the threshold voltage is important there. But we also saw that for a MOSFET, you can calculate GM in 3 different ways. So if you know the transistor parameters, you can only use ID or VGS minus VTH to go from a value of GM to your biasing parameters, your ID or VGS minus VTH parameters. Okay? Now the next question is that, okay, so I know what I want from my amplifier, but in order to keep the amplifier happy and have that current or base gate source voltage, I need a support circuit, and that's called biasing, right? So the biasing circuit puts the device where you want it, at DC. And hopefully you design it in a way that it doesn't affect your AC performance too badly. Sometimes it does, and we'll see some examples. But the biasing network should basically minimally affect the AC performance of your circuit. But it is very, very important because it sets IC or ID, which then determine the value for your GM that is going to be needed in your devices. So, the goal of biasing is to place the transistor in active region with desired terminal voltage and currents. Right? So you want to make sure that the device is in active region, and you also want to make sure that you have the desired value for the collector or drain terminal. Okay, so let's start. I'm going to talk about BJTs again. BJT biasing is slightly more complicated than MOSFET biasing for the reason that IG is 0 for MOSFET. That simple fact that IG is 0 makes your life so much easier when you're designing the biasing networks for MOSFETs. You know, the gate of the MOSFET appears as an open circuit. It doesn't affect what you do on the left side or before that. It's just an open circuit that is sampling the voltage at that node. For BJTs, the base is drawing a little bit of current. You know, sometimes that can be significant, and you need to monitor that. So I'm going to start the discussion of biasing with BJT biasing issues. Almost all of it is applicable to MOSFETs, but keeping in mind that almost always it is easier to bias a MOSFET under similar conditions. So let's assume this is the circuit that I have. And as I said, I want to establish a desired value for IC, and I'm actually not even going to tell you what is the output in this case. I'm just going to keep the device in my desired operating condition. And so I want to have the desired value of IC here. Maybe the first idea that comes to my mind is to use a proper voltage source here. So let's just call it V bias. And I know that for a BJT, IC is IS e to the VBE over VT. Okay? Now, if I choose the right value for V bias here, I notice that all of it is appearing across the base emitter junction. I should get the desired value of IC. If I know my transistor, I know it's IS. So therefore, I can see whatever IC that I want, I can just get it by setting the right value of V bias here, right, in this circuit. Okay. Think about it for a second and tell me why this is a really, really bad idea to bias your transistor. And I'll tell you in a second after that if you bias your transistor like this, you're almost always going to lose it. You're going to destruct it. Well, the reason that this is a bad idea is that we know that this IS value here is extremely sensitive to temperature variations. So you design this circuit for operation at 25 degrees. If your temperature changes to 26, 27, 30, IS will change correspondingly, and therefore IC will change by the same amount, right? So your IC is not well defined at all. It is just going to vary widely and wildly with changes in temperature, to say the least, right? Here is another problem. Once you make this circuit, design this circuit, and let's say you get the voltage source that you want, 0.732 volts, right? That voltage source, let's assume you get it. Well, if it is the only circuit that you are making in that particular application, you may get away for a little while with it as long as the temperature is not changing. But what if you want to make 1,000 of these circuits? Then each transistor will be slightly different from the other one, right? If you get 1 milliamp for 0.732 volts for this transistor, same voltage for a new transistor may give you 0.98. And then maybe another one is 1.2, and maybe another one is 0.5. You don't have control over that current, right? So there's random variation in transistor properties when you want to make many of these devices. But that sensitivity to temperature is the worst. And the reason that you can actually destroy your device if you bias it is this way is that at the beginning, let's assume that you have a cold device, 25 degrees Celsius, you connect the voltage source to it, you bias it at 10 milliamps, things seem okay for a fraction of a second. 10 milliamps goes through the transistor, well, you have voltage and current across that junction, you're going to produce heat, VI, right? You produce heat, the junction becomes warmer. When it becomes warmer, then you have a larger IS. So therefore, you have more current through the device for the same input voltage. More current means more heat. Therefore, you will get more current again. It's positive feedback. It's reinforcing itself. So you produce a little bit of higher temperature, then more current, then higher temperature, then more current, then higher temperature, and eventually you lose the device. If your power supply is ideal and can provide the current that is needed for that, right? So sometimes the power supply is limited in the amount of power that they can provide. But generally, a really, really, really bad way of designing the biasing. Now, that is one issue. The other issue is that how the designer here is going to get the voltage that they need for that V base, right? So if you go and look at these expressions, VT and IS and all those things, and you know the sensitivity of IC to the changes at VBE, you will notice that, if you want to get a stable bias current, let's say within 5% or 2% of some desired value, you have to have a voltage source for V bias that is accurate to 2 or 3 digits at least. So 0.72 volts or 0.735 volts, right? And we don't really have those kinds of voltage sources. So somebody might say that, so keep that in mind. I'm not actually going to give you the solution. That just producing that voltage that you need for biasing here is going to be a bit tricky. Okay. So that didn't work. So we are not going to do this. This is a very, very bad idea. It's a good way of making bad circuits, which you must know about them, but you shouldn't do them. So that was bad. How else can we establish an IC? The second approach that may come to your mind is from the other equation that we had. You go and remember that IC was beta IB. Okay, so what if instead of setting VBE, I set IB to something that I want? So I use a current source here to get the desired IC that I want here, right? This is going to be my I bias, and I know that in this case, IC is beta I bias. Done. I established the current that I wanted very, very easily. Stop for a second and just think about this and tell me why this is also a bad idea, a bad way of biasing. You're not going to get what you want. Okay, so I hope you thought about this for a second. The problem that you have with this circuit is this fellow here. Beta is not a well-defined parameter. Even for a given transistor, you have checked the data sheet for your labs, and you notice that beta value changes with IC and temperature and all sorts of parameters, and also between device to device. So if you make 1,000 devices, 1,000 circuits, you have 1,000 values for beta. And even for the same device, beta is going to change. If you run this device or if you operate it at, let's say, 0 degrees Celsius or 20 degrees Celsius or 40, you're going to have 3 different values of beta. So your IC will keep changing with device, with temperature, or even current. Bad idea. Bad idea. The stability that you wanted from having a known GM, a known IC, definitely doesn't seem to be likely here, right? And you have another problem here in this case that, similar to the one that we had before. In the previous situation, we had the problem of getting a very accurate power supply or voltage source. In this situation, the question is that how do I get a current source? I know voltage sources exist in nature, right? You can make a battery, or you can use a battery to produce a voltage source, although they don't give you all the voltages that you need, so we have to figure out something there. I don't know of basic current sources that I can use here. So there are some. So for example, a reverse biased photodiode can be used as a current source. But these are not convenient sources. Or I can use a reverse biased diode, but then I'm limited to a bias current of only maybe a nanoamp or so, which is definitely not enough in most situations. So using a current source here is a bit of a problem as well. These are my two ways of controlling the collector current. None of them seem to be very successful in doing it. Now, so this is also a bad idea, okay? Before moving to the next section, let's just go back and think for a second about how can I do this? How can I realize a desired bias voltage here or a desired current here? And the solution in both cases is based on using resistors. You have resistors, you almost have total control on resistor values. You use resistors or resistor combinations to realize what you need. So in this case, for example, what you do is that you go and say, you know, I have VCC to bias the device. I use a resistive voltage divider to get the voltage that I need here. Right? So this voltage here is now going to be a function of RB1 and RB2. And if you choose it right, taking into account this IB here, you can, in theory, get whatever voltage that you want at the base of that transistor and therefore bias it with whatever current that you want. Same thing here. If I know the current that I want here, what I can do is that I can go and say, well, I want this many microamps of current. I know VBE is, let's say, 0.6, 0.7 volts at that current for the IC that I need. So I know the voltage here, VB. So if I know the current that has to go through R or through this base terminal, I can figure out what RB gives me that I need. So practically you can implement both circuits, right? So you can go around the fact that you don't have any voltage source that you want, or go around the fact that you don't have current sources with convenient values or desired values. But at the end of the story, there are some fundamental issues with these biasing techniques, with both of them, that are going to haunt you, right? So what can we do? Let's look at a new circuit. Let's look at this circuit. I say I'm going to, and for, I'm not worried too much at this point about what is going on in the collector terminal. All my goal at this point is to establish the IC that I need. But you may have a resistor here or some other components. At this point in time, I'm not going to, assume that they're affecting me in any bad way. What I can do is, or one thing that comes to mind is that let's put a resistor here and see what happens. Okay. So obviously, if you have some IC, the voltage here at VB, if you want to turn the device on and put it in active region, the voltage that you need at the base is has to be such that you have accounted for the voltage drop across RE and a VBE on top of that. So you go and design the circuit like this. So this V bias, but in order to get the desired IC, you go and choose V bias like this. So you write your KVL, V bias is VBE on plus IERE, right? And you're aiming for a given IC. You can actually calculate IC right away from here. So IC is going to be V bias minus VBE on divided by beta times over beta plus 1 times RE. Sorry, beta plus 1 over beta. Okay? Now, let's look at this circuit for a while. This actually, inclusion of that resistor in the emitter circuit is going to solve a lot of those problems we had with regards to instability of the bias point. Now, for example, let's assume that you would like to have, let's say, 0.2 to about 1 volt of voltage drop across this RE. This is your typical bias condition, 0.2 volts to 1 volt. And we know that there are drawbacks for putting a lot of voltage there. So let's say somewhere between 0.2 to 1 volt is reasonable in most cases. So if that's the case, your V bias is on the order of, let's say, if you use half a volt here, it's around 1.2, 1.3 volts. Now let's see what happens if the temperature changes here. If the temperature changes, the thing that is most affected is VBE on. We saw that for a typical diode, you lose about 2 millivolts per degree centigrade of change in temperature. So if your initial, let's say, VBE on was 0.7 volts and the temperature goes up by 10 degrees, now it is going to be 0.68 volts, 20 millivolts less, right? However, look at IC. IC is not proportional to VBE on anymore. It's not exponentially proportional to those changes anymore. What happens is that you will get a slightly different IC, but V bias, remember, is now on the order of a volt or so, 1 to 2 volts, right? So a 20 millivolt change in VBE on is not going to affect you that badly. It definitely moves you away from the bias point that you had initially, but not by much. It's just a slight change because much of that change is absorbed by that V bias, right? That V bias is giving you the stability that you want. V bias minus VBE on is the number, not just VBE on. What if beta changes? So let's say you pick a transistor that has a beta of 100 and now you make the same circuit with a different transistor that has a beta of 200. Again, if you look at the expression here, well, that doesn't affect you that much either, right? So 101 over 100 is not that different from 201 over 200. So your sensitivity to beta has reduced as well. So this is mathematics, right? This is math, or the physics of the device. Let's just see, in an engineering sense, how did this RE do the magic here? Why did the inclusion of this RE in the circuit make my IC less variable, less sensitive to the changes in temperature or changes in beta and things like that? Okay, so the assumption here is that I have a fixed voltage at the base. So VB is fixed. I have a good power voltage source that fixes that VB to whatever that I want. Now let's assume that IC increases, so VB fixed. Okay? Let's say IC increases for whatever reason. So let's say something in the environment makes IC go up. What could that be? An increase in temperature. If you have a device sitting at some operating condition and the temperature goes up, your IS goes up and therefore your IC will go up. So something has caused IC to go up, or you use a new device with a higher beta and then it has a larger IC. If IC goes up, then here is your IE. IE will go up. Okay? They are connected, right? So IC is alpha IE. It's a constant relationship between them. If IE goes up, then you can show that this VE will go up. Right? The current through the resistor goes up, the voltage across it should go up. Okay? With VB fixed, if VE goes up, this means that VBE has gone down. VB minus VE has gone down, right? So let me just write it this way. VB minus VE goes down because VB is fixed, VE is going up. If VBE goes down, it pushes IC down. So what happens is that this circuit has some internal feedback mechanism now. That if something wants to move it away from where you set it, it pulls itself back towards that operating point. If IC goes up due to whatever reason, it tries to push it back down. It tries to go back to where it was as much as possible. Obviously, it's not going to cancel it entirely, but it's harder to move this circuit from where it is standing at the very beginning, right? So this inclusion of RE provided that feedback mechanism, that extra protection mechanism. So now if the temperature changes, if beta changes, your IC is not going to change that widely. And if you go back to the diode analysis circuits, the things that we had before, what you can do is that you can say, constant voltage model, I have a constant voltage drop across the diode. If I have a fixed voltage across this diode resistor combination, the current through the resistor is more or less constant. And if IE is constant, IC will be the same. You're basically making them independent of device variations and parameters. So this RE saved us, right? It made our bias point much more stable. And now you can go back to your amplifier stages and remember that we didn't want that RE for common emitter stage because that RE meant that we have to use less gain. We will get less gain, but sometimes it was there, right? So, and then, if you were wondering why we use an RE if it reduces our gain, well, this could be one reason, that you had to use that RE in order to get bias stability. We also saw that it has an additional benefit of increasing your input resistance, so you may be using it for that reason. But most likely you have an RE in your circuit for bias stability. However, we also learned about a trick through the example that if you don't like that RE that you need for bias stability, you can bypass it or bypass a portion of it and keep whatever that is required for the desired AC performance. Okay? So, good news. We found a way to make our bias point stable. Now the question is that, okay, I still don't know how to get that V bias. Right? And, now at this point of time, knowing all this stuff that we mentioned before, here is what I can do. I can go and use a resistive network to get the bias point, the bias voltage that I need, put a resistor here to get the bias stability, the internal feedback mechanism in your circuit, and over here you may or may not have a resistor. I'm not really concerned too much about the collector terminal at this end. As long as the device is in active region, I'm happy. I just want IC. Okay? Now, how do I solve this? At this point, right? So what we normally did is that we looked at the Thevenin equivalent circuit of that circuit, and you can show that IB is V Thevenin. So we said this is going to be reduced to this. And you've done this, I would say, many times by now. But let's just have it here for the sake of completeness. So V Thevenin is RB2 over RB1 plus RB2 times VCC, and R Thevenin is RB1 in parallel with RB2. Now in this case I'm looking at only one power supply, just one positive VCC at the top. In many analog circuits we have positive and negative supplies, and in a situation like that you can use superposition to find the Thevenin equivalent circuit there, right? So you can use the positive supply, apply the positive supply first, and look at the voltage, then apply the negative supply, look at the voltage, sum of them, and then R Thevenin will be the same. And if you have those values for the Thevenin voltage and resistance, you can calculate IB here to be V Thevenin minus VBE on divided by R Thevenin plus beta plus 1 times RE. Right? And then if you want to look at IC, IC is going to be beta times this, right? And I divide everything by beta. So it's going to be V Thevenin minus VBE on divided by R Thevenin divided by beta plus 1 over beta times RE. Okay? And why did I do that? I just wanted to show you the reduced sensitivity to beta now, right? So if beta changes, you have two terms that are affected by it, this one and this one. And if you want the circuit to be very insensitive to changes in beta, you just make sure that R Thevenin divided by beta is much smaller than RE. If you do that, and then what is much smaller mean? A factor of 2 or 3 smaller is all that you need to do. So the other way of looking at it is that if I step back is that I can say RB1 in parallel with RB2 should be much less than beta RE, right? And this is not a hard condition to meet, right? So if your RE is, let's say, 1 kilo ohm, you want to make sure that with a beta of 100, RB1 in parallel with RB2 is much less than 100 kilo ohm. So let's say you choose a 10 kilo ohm for RB1 and 25 kilo ohm for RB2 to meet that condition. So with that condition met, your sensitivity to beta is small, and again, because you're adding VBE to a voltage that is usually much larger than few millivolts of change that you may have, the changes in VBE are not going to affect your IC that much. So the sensitivity to, for example, temperature changes and things like that is also reduced. Okay. Now, if you look at this circuit for a BJT, for an NPN BJT, it looks like an H. This is your biasing network, right? So RB1, RB2, and RE, the three of them, they look like an H. So this is called or known as H biasing. You use a voltage divider to get the bias voltage that you need at the base, and you use a resistor in the emitter terminal to get the stability that you want for the bias point. So this is called H biasing, very popular, and at this point of time, you have solved many circuits, many problems based on this topology in your assignment and in your, hopefully practice problems as well. Now, let's do a quick bias circuit design example. So here's the example. We have so far talked about NPNs. Let's look at a PNP example in this case. So I have a combination like this here, a circuit like this here. Okay. And the question here is that design the biasing network for maximum voltage swing at the collector. So this is our output node. I want this voltage to be as large as possible, right? So the swing, the high and low of that voltage to be as large as possible. Now, the assumptions, VEB is 0.7 volts, beta is 100, VEC saturation is given, but we're going to put the device in active region. You need it to figure out what is the limit for swing, so that's 0.2 volts. VCC is 6 volts, and RC is 2 kilo ohms. Okay? Now, we want to bias this transistor such that we have the largest voltage swing at the collector terminal. As I said in previous, let's say 10 minutes ago, we usually put around 0.2 to 1 volt across this RE to absorb those changes in, let's say, beta or VBE on due to temperature variations. So let's assume that we set aside 0.2 volts here. It's a conservative amount. My voltage supply is not too large, only 6 volts. I don't want to put too much voltage across RE. So let's assume that I use that 0.2 volts across this resistor to give me the bias stability that I need. Okay, with a VEC saturation of 0.2 volts. What that means is that I have about 0.4 volts that I need to leave for the resistor in the emitter and the collector emitter terminal voltages. So from here what I can see is that VC max, the collector voltage, the maximum collector voltage that I can have is 6 minus 0.2 minus 0.2. VCC minus these two voltage drops, right? So that's 5.6 volts. That's the largest voltage that I can have at the collector. What is the smallest voltage that I can have at the collector? Well, the voltage at the collector can keep going down until it hits the ground, right? When does that happen? When IC is 0. So that's the cutoff edge, that's the cutoff current. So maximum swing is from 0 to 5.6 volts, right? So this is the range of voltages that I can have. Now the question is that, okay, so if I know this is the maximum values, right, so I can vary the voltage at the collector from 0 all the way to 5.6 volts, where do I bias my transistor? Where do I keep the transistor normally if I want to take advantage of all that range? Well, the answer is that you want to put the device in the middle of that range. So the bias point is going to be the middle of your minimum and maximum values. So maximum is 5.6 volts, minimum is 0 volts, you put it in the middle, so that's 2.8 volts, right? So VC at the bias point without any small signal coming in, you wanted to put it at 2.8 volts. What happens now is that you have 2.8 volts to go up, because remember that maximum voltage was 5.6, and 2.8 volts to go down. So that's the largest swing that we can have. Okay, so if that's the case, that actually gives me IC, because I know this RC is 2 kilo ohms. It was given in the problem. If I know the voltage at the top of that resistor, I can calculate IC. IC is going to be VC over RC, and that's 1.4 milliamps. Okay, so I established what bias current I need. All right. Now I can actually figure out the voltage drop here. I already have it. The voltage drop between the emitter and base I already know. I can figure out the voltage at the base. The voltage at the base, VB, this voltage, is going to be VCC minus the voltage drop across the resistor minus VEB. So VCC minus VRE minus VEB. And I'm assigning 0.2 volts for VRE, and VEB is given 0.7 volts. So that's 6 minus 0.2 minus 0.7. That's 5.1 volt. So I want to choose R1 and R2 such that I get 5.1 volt at base. Okay. Now, I can do two things here. I can look at this IB and I can calculate IB. IB is IC divided by beta. So 1.4 milliamps divided by 100, that's 14 microamps, right? So what I can do is that I can show, well, let me just draw the Thevenin equivalent circuit here. I want 5.1 volts here. So there's going to be a Thevenin equivalent circuit and a Thevenin equivalent resistance, which is R1 in parallel with R2. Let me just be explicit about that. And V Thevenin here. That is going to give me 5.1 volts once you take this IB through it, right? So this is not too difficult. I can actually do the math here. You can show that VB is IB times R Thevenin, so R1 in parallel with R2, plus V Thevenin. But V Thevenin we know is VCC times R1 over R1 plus R2. Okay? So I know this equation, I know VB, I know IB. I need to choose values for R1 and R2. I can choose any value for one of these resistors and then figure out the other one from this expression here, right? So for example, you can choose an R1 of 1 kilo ohm and then go and calculate R2. Or in this circuit, if I want to make my life easy, I notice that I want 5.1 volts. So what I do is that I choose 5.1 for R1 and 0.9 for R2, and that gives me 5.1 volts. That's a bit, so how you choose the value. In general, what you want to do is that you want to make sure the current that goes through this branch, let's just call it IBB, is much larger than IB. And the reason for that is that you don't want a small change in IB to change the voltage at the base voltage. If you pass a lot of current through R1 and R2, and that means like 10 times IB or 5 times IB, not 1,000 times IB. So if you pass more current through R1 and R2, you can see that when you look at the voltage at the base, it's becoming less and less dependent on IB. So you choose the values of R1 and R2 such that you get a stable voltage here, right? So if your IB is 14 microamps, let's say I choose IBB to be 10 times IB, okay? And therefore, IBB is going to be 140 microamps. And with that known, and knowing that the current here is different from the current here, right? Because IB adds to it. But now I'm getting a range. So with that known, I can say that R1 over R2 should be about, let's say R1 plus R2 should be about VCC over IBB. So I have a value for what I want the sum of these two resistors be, and then I choose one and I pick the other one accordingly. So in this case, let's say IBB is 140 microamps, VCC is 6 volts, so I can see that R1 plus R2 should be about, let's say, 42 kilo ohms, right? And I go and choose the right value so that I pick one of them, and or now I have two equations actually. I can solve it and figure out what it should be. One thing that you can do practically in most cases is that just keep this rule in mind, that you want IBB to be about 10 times larger than IB. And if that's the case, you can assume that IB doesn't affect the voltage at this point that much. If that's the case, just choose the values of R1 and R2 such that you get your 5.1 volt at that node. Then if you are really concerned about the accuracy of your calculation, you can do the analysis with the chosen values for R1 and R2, or do a simulation. Now you can do the simulation now, right? So you have R1 and R2 values, and then you have to move slightly above that region, up or down, in order to get the values that you want for the current. So let's say you want to choose E12 values, you just go and play around what you chose initially. But that's the process, right? So usually for biasing, you assign the biasing point is IC that you need to worry about because that gives you GM, and voltage swing because that tells you how far you are from the edge of saturation or cutoff. And in this case we wanted maximum swing, so we just put the bias point in between the two voltage rails. Sometimes you want a smaller amount of swing, so you can put the bias point closer to ground or closer to VCC depending on the situation. But once you determine those desired values, you go and design the bias network according to that. Okay. So now let's go and look at another biasing technique, which is called self-biasing. So here is an example. Oh, it's not an example. This is another biasing technique altogether. And in this case, what we do is we go and take a resistor, put it between the base and collector of the device. And again, this is a circuit that I'm hoping you have solved by now for your DC analysis. But let's just quickly solve this circuit and see what happens. My goal is to find IC. So if I write a KVL going from VCC around the transistor, because I don't want to go across VCE, I don't know that, I go around this, I notice that this current is IB and this current is IC plus IB, right? Because it splits into these two currents. So I write my KVL is RC times IC plus IB plus RBIB plus VB. And if I go and calculate IC from here, I can see that IC is VCC minus VBE divided by RC times 1 over beta plus RB divided by beta. Okay? And again, you can see that, because VCC is usually much larger than VBE, small changes in VBE are not going to affect the numerator here that much. A few millivolts of change in VBE doesn't change VCC minus VBE that much. The effect is absorbed by VCC. And then if you have changes in beta from, let's say the fact that you're using many different devices or the temperatures change or things like that, as long as RC is much larger than RB over beta, then those changes in beta, a factor of 2 change in beta is not going to change your current by a factor of 2. So this is what the math tells you. But let's see again, from the engineering sense, what happens here? What is causing this behavior? What is making this circuit more stable, less sensitive to those changes in, let's say, parameters in your circuit or around your circuit? So again, assume that we have established the desired biasing point here for this circuit, and for some reason, IC goes up. Why does it go up? Again, your beta has increased or your temperature has increased. IC has gone up. So, as soon as IC goes up, what happens is that VC, the voltage here, VC, which is VCC minus ICRC, will go down, right? IC has gone up, VCC is fixed, the voltage drop across the resistor will increase, and therefore VC will go down. When VC goes down, then what you can see is that IB, which is VC minus VB divided by RB, will go down. Why? Because VB is more or less fixed. VB is VBE. In this case, let me just write it as VBE maybe. And if VC goes down, the other end of the resistor is more or less seeing the same voltage. Remember, the diode voltage doesn't change much with its current. IB will go down. As soon as IB goes down, it pulls IC down with itself. So again, like the situation that we had before, if IC wants to go up due to some external parameter, some external issue, the circuit will pull it back down or try to pull it back down to the original location. It doesn't let it move from that point by much. And these two techniques are basically your two biasing techniques that you can use for your common emitter, common base, common collector stages. However, if you're using the H biasing, you get your original stages back, right? So you can just separate the biasing and then look at what is happening between the biasing and, network at the input and maybe the load, and say this is my common emitter stage or common collector stage, or so on and so forth. With this stage, you cannot do that. With this biasing, you cannot do that. This is called the self-biased circuit, because I cannot really separate the biasing from the input and output here, right? If your input comes here and output is taken from here, your biasing is sitting between them. Your biasing is letting a little bit of input to go to the output, or a little bit of output to be fed back to the input. And for that reason, I cannot use the formulas if you're using this biasing technique. It's nice because you use only one resistor to get a stable bias point, but in terms of circuit analysis, you have to go back to your small signal models in order to analyze this circuit. Now, what I would like you to do is to go to, I think, slide number 49, but it might be a bit different in your notes. But go to this slide. And here are 4 connections of load and source to your amplifier stage. So in this case, I have a common emitter amplifier for the first 2 on the left, a common base stage for the middle one, and this one is also a common base stage. So 2 common emitter amplifiers on the left, 2 common base stages on the right. What I would like you to do is to look at these circuits and figure out why you don't want to bias these amplifiers in these configurations, right? So what is wrong with the first 2 on the left and then the other 2 on the right? And then maybe think about a solution for fixing those problems. Okay? And if you have questions, you can of course come and see me during the live sessions or office hours to discuss these problems. Now, with the MOSFET, I'm going to switch to slides now. With a MOSFET, the biasing techniques are very similar. However, they're even easier than the situation that you had with BJTs. Again, with a MOSFET, you go and decide what ID is it that you want to give you the desired GM. Maybe you go and figure out what is the VGS minus VTH that is needed as well. Figure out what is the drain voltage that you need, for maximum swing or maximum gain or whatever parameter that is given to you. And you go and design an H-bias network like this. There's, of course, more details in your textbook. You can also use the self-biased network here as well for MOSFETs. Now, the issue here is that because IG is 0, the voltage drop across RG is 0. And, if there's no voltage drop across RG, maybe a question that you can ask yourself is, well, if the voltage drop across this resistor is 0, if the current rate is 0, why do I need a resistor there? Why don't I just short circuit the drain to gate? What would I lose if I do that? And think about it. And a hint to you is that if you do that, you cannot use this as an amplifier in many cases. So the DC part is going to be okay. You will lose something on the AC port. And maybe think about one of those amplifier stages and see if that can be done. We didn't talk about current sources and designing current sources. We don't do this much at discrete circuit because you have cheap resistors available to you, so you get whatever that you want from your resistors. Now, here is an example of a complete common emitter stage. We actually have solved a common source stage. We actually have solved this circuit with a BJT. It's going to be very similar. You do the DC analysis and then small signal or formulas afterwards. Make sure you do a lot of these problems. You solve at least 4 or 5 of each one of these categories to feel comfortable and actually be able to do it quickly enough. We didn't talk about the frequency response that much in this course. The issue is that once you're using coupling capacitors in a circuit like this, you will not be able to pass very low frequency information from your source to your load. So there's going to be bandwidth issues at the bottom end of the frequency domain. You know, FL is set by the coupling capacitors and then maybe bypass capacitors. Then you have a region that is flat gain. This is where we have focused so far. But at very high frequencies, you're going to have problems again, right? So again, your transistor is not going to be fast enough for amplification at very high frequencies. So that we haven't talked about. And then you have examples for amplifiers. And the goal here is that for you to go and figure out, you know, I would suggest solving a few of these with the small signal model, but you can also then go back and see that, okay, this circuit actually can be redrawn as this for AC. I'm going to draw the AC circuit, right? So this is V out, RE, RC. Now, if C1 is short-circuited to ground, then this is going to be R2. And R1 is now going to be between base and ground. So remember it was here, so it can be put down here. And then you have RS here and VS. Okay. Now, the original circuit looks very scary, but the good news is that now I can look at this as a basic common emitter stage, right? So this combination is your common emitter stage with emitter degeneration. You know the input resistance to here, you know the output resistance to here. The only change is that this RC, for those formulas, now you have to use RC in parallel with R2. Now you have two resistors for that value. But now you can use all those formulas, right? And then, you know, what is the voltage that appears here? Well, it's the input resistance that you have, R in and R out, let's call it. You can find them from the formulas and then put that input resistance in parallel with R1 and look at the voltage divider between that combination and RS to figure out what is VI and so on and so forth, right? This is another example. So for the AC circuit here, what I can show is that the circuit is going to look like this. So the DC source is grounded. The DC current source here is opened. R2 between the emitter and the top of C2 is now going to be appearing like this. This is RC. And then R1 is going to be between base and, because C2 is grounded, between base and ground, R1. And then I have my RS because C1 is also shorted. And again, I'm back to my basic common emitter stage here. And so if you look at this part, this is my common emitter with emitter degeneration. I know the input resistance. I know the output resistance. I can go and use formulas to replace that with, you know, the triangular shape that we had and solve it. I'm going to leave this one to you as an example for your practice, but the hint here is that you can replace this entire part with the equivalent input resistance that you see when you look into the emitter of Q2. So figure that out and then you plug it in here, and then what you have here is a basic stage that you already know. This one I'm going to again let you solve it, but here is a hint. It's not a common emitter stage. Figure out which one it is. This is again a stage that you should be able to solve using the formulas, but maybe a bit more complicated. So definitely try these, but come and see me during the live sessions or office hours if you would like a little bit more help with the solution. And again, in here, the AC circuit will have a ground at this node, separating R1 and R2 from each other. R2 will appear in parallel with RE, and then you have an input resistance going in here, an output resistance going back here, and you can identify the stage and use the formulas. As I mentioned, I have put a whole bunch of midterm and final exams with solutions online that you can use as examples. Please do not study them. Try them first and then check your answer. Do not study solutions. There are so many combinations for problems here that if you study all of them, you still will not be able to solve the problems in